an IITG person promises only what he can deliver, and an IITG person delivers what he promises.
So, today we are going to study about multi-degree of freedom systems. In the previous classes we have studied about the free and force vibration of single and 2 degrees of freedom systems. In case of single degree of freedom systems, we have studied how to find the response of the system, and in case of 2 degrees of freedom systems, we have also find the response of the system for free and force vibrations. We have used different methods to find the equation motions. The equations motions are found by using either Newton's method or D'Alembert principle, or by using the energy principle, which include Lagrange principle and Hamilton's principle. Either we have used Hamilton principle or extended Hamilton principle depending on the systems. So, for a conservative systems we have used Hamilton principle, and for non-conservative system one can go for this extended Hamilton principle. And by using Lagrange principle you can derive the equation motion for multi-degree of freedom systems, and by using this Hamilton principle, though you can find the equation motion for any type of systems, but particularly it is useful for continuous systems. Similarly, this Lagrange principle is particularly used for multi-degree of freedom systems, and if the number of coordinates or number of degrees of freedom is less than 2, or if it is a single degree of freedom or it is a 2 degrees of freedom system, either you can go for this energy based principle or you may go for this Newton's or D'Alembert principle. But for higher systems or for systems more than 2, you should go for Lagrange principle to derive the equation motion. If the system is a continuous system or distributed mass system, you should go for extended Hamilton principle. And now we will study about this multi-degree of freedom systems. So, multi-degree of freedom systems are one in which you require 2 or more coordinates to describe the motion of the system. Already you have seen the case of a double pendulum, and if you take a double pendulum, so it is a 2 degrees of freedom systems. So, for more than 1 degree of freedom system, it is a multi-degree of freedom systems. So, already you know how to write the equation motion. So, for that previously I told about different types of coordinate systems. One is the physical coordinate system, and second one is the generalized coordinate system, and third one is the principal coordinate systems. So, in case of physical coordinate system, you can put any physical coordinates to describe the motion of the system, and in case of generalized coordinate system, these are the minimum number of coordinates required to express the motion of the system. So, the relation between these generalized coordinates and the physical coordinates, you know, by using the number of constraints you can describe the, if let n is the number of generalized coordinates and m is the number of physical coordinates. So, your m will be equal to n plus number of constraints. Let c is the number of constraint. So, m will be equal to n plus c. N is the number of generalized coordinates and c is the number of constraints. So, in this case, in case of this double pendulum, you may write the equation motion by using these coordinate, physical coordinate x1, y1, x2, y2, x2, y2. So, these are the physical coordinates you can use. So, or the generalized coordinates will be either you can write the x displacement of this bob 1 or this mass 2. So, either you can use this theta 1, theta 2 as the generalized coordinates, or you may use x1 and x2 as the generalized coordinates in this case of double pendulum, but you may use x1, y1, x2, y2 are the physical coordinates of the system. So, this length is constant. So, this length equal to x1 square plus y1 square equal to L1 square, and similarly this length L2 equal to x2 minus x1 square plus y2 minus y1 square root over. So, these are the constraint equation. So, you have 2 constraint equation and 4 physical parameters. So, you have number of coordinates, generalized coordinates equal to 2. So, this is a 2 degree of freedom system, and you have 2 generalized coordinates to describe this motion of this system. Already I told you, by putting the coordinate system at different places you can get different equation motion. So, when the equation motion, in the equation motion you can write the equation in this form, you can write it in this form mx double dot plus kx equal to f. So, here m is the mass matrix, k is the stiffness matrix, and f is the force vector. So, this when this mass matrix, so let me write for a 3 degree of freedom system, this mass matrix will look like this. So, m11, m12, so it will be m11, m12, m13, m21, m22, m23, and m31, m32, m33. So, this is the mass matrix for a 3 degree of freedom system. So, if all the components of this mass matrix are present, or if some of the off diagonal elements are present, then this mass matrix is known to be coupled. So, this is coupled mass matrix, and the system is known to be dynamically coupled. Dynamically coupled. Similarly, if the stiffness matrix you can write this stiffness matrix for this 3 degree of freedom system in this way: K11, K12, K13, K21, K22, K23, and K31, K32, K33. So, by using, or if these all the elements or the off diagonal elements are present in addition to the diagonal elements, then this is known as statically coupled. So, if by using some coordinates you can decouple this mass matrix and stiffness matrix, those coordinates are known as the principal coordinate of the system. So, for the coordinate system for which you are getting a dynamically uncoupled and statically uncoupled system, then those coordinate system is known as principal coordinate system. So, you have 3 different coordinate systems. One is the physical coordinate system, second one is the generalized coordinate system, and third one is the principal coordinate system. So, by using principal coordinate system you can reduce this equation motion to that of 3. For a 3 degree of freedom system you will get 3 different equation motion, uncoupled equation motion. So, first equation will be m1 x1 double dot plus k1 x1 will be equal to f1. Second equation will be m2 x2 double dot plus k2 x2 equal to f2, and third equation will be m3 x3 double dot plus k3 x3 equal to f3. So, if you have principal coordinate, if you are using principal coordinate, then x1 y1 principal coordinate x1 x2 x3, then you will get a set of uncoupled equation. So, this is uncoupled equation, and these equations are same as the equations you have seen for a single degree of freedom system. So, as you are reducing this equation to that of a single degree of freedom system, so you can find the response of the system very easily. When these equations are uncoupled, then also you can find the equation motion, then also you can find the response of the system by using different methods. So, for a 2 degree of freedom systems already we have seen how to find the response of that system. So, in that case we have used this normal mode method. So, we have defined the system response in terms of normal mode. So, normal mode is nothing but this is the free vibration response of the system when we are assuming all the masses are passing through the equilibrium position at same time and they have the same frequency. So, we have assumed in case of 2 degree of freedom system, we have assumed the solution in this form. So, we have assumed x1 equal to x1 sin omega t and x2 equal to x2 sin omega t. So, we have assumed this frequency of both the modes x1 and x2 to be same, but their amplitudes are different x1 and x2 and they have same phase, that means they are in phase. So, in case of normal mode we are assuming that all the particles of the system are moving with same frequency and passing through the equilibrium position at the same time. So, for multi degree of freedom system also we can extend this idea from the second degree of freedom system and we can write the normal mode x3 or x4 x5, in that way we can write. So, x3 will be equal to, so small x3 I can write equal to capital X3 sin omega t. So, there are many systems which you cannot model it as a single degree of freedom system or 2 degrees of freedom system. In that case you should model it as a multi degree of freedom system. Let us take the example of a 10 story building. So, in this 10 story building subjected to this air force, so wind force. So, if it is subjected to wind force or it may be subjected to some earthquake. So, you want to find the response of the system, response of this building. So, what will happen to the building in case of this wind or when it is subjected to the earthquake. So, in these cases if you want to study the response of the system, so you cannot model it as a single degree of freedom system or 2 degree of freedom system. In that case you should go for multi degree of freedom system, in which you may have a mass matrix for this 10 storied building. You may have a mass matrix of 10 into 10, 10 is to 10 and a stiffness matrix of 10 is to 10, and this force vector depending on where the force is acting you may have a force vector. So, the force vector will be a 10 is to 1 force vector you may get. Similarly, for other systems you may have a system with 100 degrees of freedom system or you may have 1000 degrees of freedom system. So, in those cases you cannot solve these equations by using this single or reducing it to a single or 2 degrees of freedom system. So, that time you should apply some other methods to solve these equations, and you can extend the methods what we have studied in 2 degrees of freedom system in this case also. So, in this case you can write the equation motion in this form. So, you are writing equation motion mx double dot plus kx equal to f. So, f equal to 0 is for free vibration, and when you are taking f equal to some forcing function then it will be a force vibration system. So, let us study first the free vibration response of the system. So, mx double dot plus kx equal to 0 is the equation for this free vibration. So, in this case you can find or you can pre multiply this m with m inverse. So, m inverse mx double dot plus m inverse k x equal to 0, you can write in this way this equation, and this m inverse m is this identity matrix. So, I x double dot plus this m inverse k, let me write equal to a. So, a x equal to 0, and now I can assume the normal mode in this form. So, x I can write equal to, let x equal to capital X. So, x equal to capital X sin omega t. I can take sin omega t, or I may take also x equal to x e to the power omega t. So, by assuming x equal to x sin omega t and substituting this equation in the main equation, the previous equation, I can write this equation in this form. So, it will becomes, so x double dot will becomes minus omega square x sin omega t or minus omega square x. So, this above equation will reduce to this form. So, it will becomes a minus omega square x, a minus omega square. So, a minus omega square I into x or x sin omega t, I can write it is x sin omega t equal to 0. So, for non-trivial solution, that is when the response is non-zero, that time you can find this a minus omega square I, so a minus omega square I x equal to 0. So, this omega square let me put equal to lambda. So, this equation is reduced to in this form, this is the known form of this eigenvalue function. So, we have studied this equation in case of 2 degrees of freedom system also. So, in case of multi-degree of freedom system also, this system is reducing to this eigenvalue problem, where you have to find the eigenvalue of matrix A to find this lambda. So, lambda are the eigenvalues. So, lambda are the eigenvalues and x will be the eigenvector. So, you can find the eigenvalues and eigenvectors of this matrix A. So, A is nothing but it is the M inverse K matrix. So, first find A matrix and then find the eigenvalues and eigenvectors of this matrix to find the free vibration response of the system. So, by using this eigenvector, so these eigenvectors correspond to the normal mode of the system. So, by finding the normal mode of the systems, you can find the free vibration response of the system if you know the initial conditions. Already we have seen in case of a 2 degrees of freedom system, the resulting free vibration x at any time t can be written as C1 phi 1 plus C2 phi 2. So, where phi 1 and phi 2 are the normal modes of the system and C1 and C2 are the modal participation in the resulting free vibration, which depends on the initial conditions. So, by knowing these initial conditions, and you can find by knowing the initial conditions and the modal matrix will come from this eigenvector. By knowing this eigenvector, you can find the modal matrix, and by using this modal matrix phi 1 phi 2. So, if you are taking only 2 modes, you can take phi 1 phi 2, and when you are taking multi modes, then it will be phi 1 phi 2 C3 phi 3 and C4 phi 4. In this way, it depends on the number of modes you are taking. So, the resulting free vibration will be resulting free vibration x. So, this is the free vibration response will be the summation of different modal frequencies, where phi 1 phi 2 phi 3 are the eigenvectors for the correspond to first mode, second mode and third mode respectively. So, in this way you can analyze or you can find the free vibration of a system by using this normal mode method. Similar to the 2 degrees of freedom system, first you should find the A matrix. A is nothing but M inverse K. First find M inverse K, that is A. So, A equal to M inverse K. So, after writing the equation motion, you will get the mass matrix M and stiffness matrix K. By using M inverse K, find the A matrix and find the eigenvalue of A matrix and eigenvector of A matrix. So, eigenvalue will give you omega square. So, from omega square you can find omega, the frequency of the system. So, for a multi-degree of freedom system, you will get number of frequencies. So, if you have a 3 degrees of freedom system, you will get 3 value of lambda. So, you will get 3 natural frequencies of the system or 3 normal frequency of the system. So, corresponding to these 3 normal mode frequency, you will get 3 modal amplitude, or you will get 3 modal values or eigenvector. So, corresponding these 3 eigenvector or normal modes. So, you can find the free vibration response of the system. So, for finding free vibration response, use the superposition principle of the normal modes. So, let you have 10 modes. So, in that case you can write the free vibration x will be equal to summation I equal to 1 to 10 Ci phi I. So, where phi I correspond to phi I equal to xi, or it is equal to x at lambda equal to lambda I. So, in this way you can find the free vibration response of a system. So, you may use some other method to find this x, that is the normal mode. The normal mode you can find using from the adjoint matrix of the system. So, you can write this A minus lambda I by using this adjoint matrix method also you can find. Let me write B equal to A minus lambda I. So, if B equal to A minus lambda I, then I can write this B inverse equal to, so 1 by B, 1 by determinant B into adjoint B, B inverse equal to 1 by determinant B into adjoint B. So, if you pre-multiply this determinant B into B in this equation, determinant B into B inverse. So, this will be equal to determinant B, B, and this is determinant B and then adjoint B. So, already you know B into B inverse is the I matrix. So, your B into I, so determinant B into I, so this will be equal to, so this cancel, so this becomes B into adjoint B. So, B into adjoint B matrix. So, already you know your B equal to, we have written this B equal to A minus lambda I. So, A minus lambda I, A minus lambda I determinant into, so into I. So, this is I equal to, so in that way you can write, so this will be equal to B equal to A minus lambda I, A minus lambda I into adjoint A minus lambda I. But already you know that this A minus lambda I, for lambda to be the eigenvalue, this A minus lambda I, determinant of A minus lambda I equal to 0. So, you can write this equation. So, A minus lambda I into adjoint A minus lambda I equal to 0, but you know this A minus lambda I into x equal to 0. So, if you compare these two equation A and equation B, if you compare, then you can write your x equal to adjoint A minus lambda I. So, you can find this eigen vector of the system by finding the adjoint of A minus lambda I matrix. So, easily you can find the eigenvector by using this adjoint A minus lambda I. By using MATLAB also very easily you can find the eigenvalue and eigenvector of the system. So, in MATLAB you have this function. By using MATLAB you have this matrix M, you have this matrix K, M is the stiffness matrix, K is the M is this mass matrix and K is the stiffness matrix. So, you can write this code like this. So, you just write find the A. So, A equal to M inverse. So, INV M and multiplied by K. So, this will give you A matrix and you can find, you just write V D. So, by writing this V D equal to EIG A. So, this will give you this V matrix. So, V will contain the eigenvalues and D will contain a diagonal element. So, this diagonal element are the eigenvalues of the system. So, D will contain the this diagonal element will contain the eigenvalue and this V will contain the eigenvector. So, by using this MATLAB also you can find the eigenvalue and eigenvector. So, when you are doing it by hand or manually for a lesser degrees of freedom system, you may use this adjoint matrix method. So, adjoint A minus lambda I you just find to find these normal modes of the system. So, let us take one example. So, we will take the example of a simple 2 degrees of freedom system. Let us take a 2-rotor systems what we have studied before. So, already you know that this 2-rotor system is a semi definite system. So, in case of semi definite system, 1 of the natural frequency equal to 0 and you have a rigid body motion. So, let us take this system for simplicity. Let I1 is the inertia of this rotor and I2 is this inertia and K is the stiffness of this rod. So, you can write this is theta 1 generalized coordinate theta 1 and theta 2 assigned to these two rotors. Now, you can find the normal modes. So, let us find the normal modes by using this adjoint matrix method for this case. So, in this example, so the equation motion already you have found by using different methods. So, the equation motion if you will write it, so it will be like this. So, it will be I1 0 0 I2 theta 1 double dot theta 2 double dot plus K minus K minus K plus K theta 1 theta 2 equal to 0 0. So, this equation motion either you can find by using this Lagrange principle. So, in case of Lagrange principle, so the kinetic energy T equal to half I1 theta 1 dot square plus half I2 theta 2 dot square and the potential energy U. So, if you are using the stiffness of this, so it will be equal to half K into theta 1 minus theta 2 square. So, by using this kinetic energy and potential energy, so you can find Lagrangian of the system, that is equal to L equal to T minus U, and then by using the Lagrange principle, that is d by dt of del L by del Q k dot minus del L by del Q k equal to 0. So, as there is no force acting on the system, you can take this as a free vibration. So, this forcing part equal to 0 or this non-conservative forcing Q k equal to 0. So, this equation reduces to this form, and by using this Lagrange principle you will get this equation. Also, you may use this Newton's method, and in which by drawing the free body diagram of this mass or this inertia 1, rotor 1 and rotor 2, you can find the equation motion. So, it will be, it can be written in this form. So, here your mass matrix equal to I1 0 0 I2 and the stiffness matrix K equal to K minus K minus K K. So, after finding this mass matrix and stiffness matrix, you can find the A matrix. So, A will be equal to M inverse K. So, you can find the inverse of this matrix and you can find this M inverse K, and this M inverse K is nothing but, so you can get it like this. So, it is equal to K by I1 minus, so K by I1. So, in this way you can write A minus lambda I matrix if you want to write, or A matrix if you want to write. So, this will be equal to K by I1 minus K by I1. So, this is minus K by I2 and K by I2. So, if you want to write A minus lambda I matrix, so A minus lambda I will be equal to K by I1 minus lambda minus K by I1 and minus K by I2. This is K by I2 minus lambda. So, the diagonal elements are subtracted by this lambda and you got this A minus lambda I vector. So, A minus lambda I matrix you got. So, after finding this A minus lambda I, so if you want to find the eigenvalues, so you can find that thing by finding the first the characteristic equation. So, this characteristic equation is equal to A minus lambda I, determinant of A minus lambda I equal to 0. So, you substitute determinant of A minus lambda I equal to 0, that will give you the value of lambda, and this x, that is the eigenvectors, you can find by finding the adjoint matrix of A minus lambda I. So, by finding this determinant of A minus lambda I equal to 0, so this equation will becomes K by I1 minus lambda into K by I2 minus lambda minus, so this into this minus this into this. So, in this way you can find A minus lambda I, determinant of A minus lambda I will give you So, you will get this equation k by I1 minus lambda into k by I2 minus lambda minus, so minus minus and then 1 minus. So, this becomes k square by I1 I2. So, this is, so you multiply this. So, this is k square by I1 I2. So, this equation you can write in this way. So, it will becomes k square by I1 I2. Just look here, this multiplied by this, then minus lambda into k by I1 minus lambda into k by I1, again from this minus lambda into k by I2 minus lambda into k by I2, and then next term is lambda square. So, plus lambda square minus k square by I1 I2. So, this plus and this minus cancel. So, you can take, so this is minus lambda k by I1. So, this equation becomes lambda square minus lambda, if I will take common, this is k by I1 plus k by I2. So, the characteristic equation reduces to lambda square minus lambda into k by I1 plus k by I2 equal to 0. So, or lambda into lambda. So, if I will take lambda common, so this becomes k by I1 plus k by I2. So, this, so lambda into lambda, so this equal to 0. So, lambda equal to 0, either lambda equal to 0 or, so this part equal to 0 or this part equal to 0. So, either lambda equal to 0 or lambda equal to k by I1 plus k by I2. Already you know in the previous class that this is a degenerate system in which one of the natural frequency equal to 0, which you have obtained here, and the second natural frequency you are getting, that is equal to k by I1 plus k by I2. So, this is lambda. So, frequency will be root over this. So, this will be equal to k by I1 plus k by I2. So, your eigenvalues are 0 and k by I1 plus k by I2, and now you have to find the eigenvector. So, you can find eigenvector in many different ways, but just now we know that we can find it by finding the adjoint of A minus lambda I. So, we know our x will be equal to adjoint A minus lambda I. Already we got the value of lambda. So, one value of lambda equal to 0. So, by substituting this value, so let us find. So, it will be equal to, so when lambda equal to 0, adjoint A minus lambda I. So, I can write this equal to adjoint A minus lambda I. Already we know what is A minus lambda I. So, this is equal to k by I1 minus lambda. So, lambda I will put equal to 0. So, this is 0 and this is 0. So, it will be k by I1 minus k by I1. So, I can write in this way. So, this will be minus, so this is k by I1 minus k by I1 minus k by I2 k by I2. So, I have to find the adjoint. So, as lambda equal to 0, I have to find the adjoint of this matrix. So, adjoint of this matrix equal to, so I can write first the cofactor matrix, and transpose of the cofactor matrix will give the adjoint of this matrix. So, for finding the cofactor of this matrix, so for this position, you can find the cofactor by suppressing this and this. So, it becomes k by I2. So, it becomes k by I2. So, for this position it will be, so negative of, so this row and this row you suppress. So, this becomes minus plus. So, this becomes k by I2, and for this position, okay, for this position you can find. So, this will becomes minus k by I1. So, this becomes k by I1, and for the last position it will be k by I1. So, this will be the transpose of this matrix equal to transpose of this matrix. So, it will becomes k by I, so k by I2, this becomes k by I2, k by I1, and k by I2 and k by I1. So, you just note from this that the first column contains k by I2 and k by I2, and in the second column it contains k by I1 and k by I1. So, if I will normalize or by making this second, so this x is nothing but your theta 1 and theta 2, that is the amplitude of theta 1 and theta 2. So, this amplitude theta 1 and theta 2 or x1 and x2 I have written for that. So, this becomes so x1 and x2. So, either you take the first column or the second column. So, if you are taking the first column or second column, you can observe that by keeping this x2 equal to 1. So, this will reduces to 1 1 1 1. So, I am normalizing this with respect to x2, or I am keeping this k2 k by I2 equal to 1. So, by keeping this I can write this adjoint A minus lambda I equal to 1 1. So, this is the adjoint A minus lambda I. So, your x1 and x2 you can obtain by taking any column of this adjoint matrix. So, you can observe that both columns, the normalized value of both columns are same. So, you take any column to find the normal modes of the system or find the eigen vector of the system. So, eigen vector becomes 1 1. Similarly, you can find for the other case. So, for the other case also you can find the normal mode, and in that case you can find the normal mode. So, it will become, so your x will be equal to k by I1 minus lambda minus k by I1 minus k by I2, and this becomes k by I2 minus lambda. So, here I have to substitute lambda equal to, so for the second mode, so you have checked that this lambda equal to k by I1 plus k by I2. So, I can write this k by I1 plus k by I2. So, in this case if I will substitute this thing, so k by I1 minus k by I1 will cancel. So, this becomes minus k by I2. So, this x becomes, so you have to find the adjoint of this matrix. So, x equal to adjoint of, so adjoint of minus k by I2, and so this becomes minus k by I2 and this is minus k by I1. So, this is minus k by I1, and this position it becomes minus k by I2 minus k by I2, and in the last position, so this becomes k by I2 minus lambda. So, lambda I am putting k by I1 plus k by I2. So, this k by I2 cancel. So, minus k by I1. So, this becomes minus k by I1. So, you have to find the adjoint of this matrix. Already I told you how to find this adjoint of this matrix. So, for finding adjoint of a matrix, you have to find the cofactor matrix, and transpose of that cofactor matrix will give you the adjoint of that matrix. So, by finding that thing you can write it in this form. So, it will becomes, so this will, so the cofactor matrix becomes, so cofactor matrix, okay. So, you just find the cofactor matrix. So, that will becomes minus k by I1, and for this position this becomes minus k by I2. So, this becomes plus, and for this position it becomes k by I1 become plus, and for this position it becomes k by minus k by I2. So, minus k by I2. So, transpose of this matrix. So, transpose of this matrix will become, so this will nothing but this is minus k by I1, and this becomes k by I2, and it will becomes k by I1 and minus k by I2. So, in this case also you just observe that both columns, if you normalize that thing, will be same. So, you take any of the column and you normalize that thing. So, in this case you will get it equal to, so your x1 x2 will become minus I2 by I1 and 1. So, in this case you just observe that this amplitude ratio are inverse of the inertia ratio. So, if you know the inertia of the system, so in that case you can find the amplitude of the system by using this relation. So, from this two rotor system you have observed that, so if you have a two rotor system, so in the fast mode, that is the rigid body mode, that lambda equal to 0. So, you have observed that this x1 x2 equal to 1 1. So, in that case it becomes both are rotating with same amplitude. So, when it is rotating with theta equal to 1, so this side also rotate with same theta, that is equal to 1. And in the second mode, when this is rotating in this direction, in clockwise direction, this will rotate in anti-clockwise direction. So, for that reason you have this minus sign, and this theta 1 by theta 2 will be theta 1 by theta 2 will becomes negative of this I2 by I1. So, in this way you can find by using the normal mode the mode shapes of the system. So, by using this adjoint matrix method also you can find the eigenvectors of the system. So, let us see another method to determine the equation motion of a multi degrees of freedom system. So, that is the influence coefficient matrix method. Influence coefficient method. This is a very powerful method to find the equation motion of a multi degrees of freedom systems. So, before going for that, so we should see different definitions. So, what is the influence coefficient, displacement influence coefficient or stiffness influence coefficient, that thing first we will see, and then we will use this influence coefficient method to derive the equation motion of a system. So, you know the force of a system, if you are writing in this form force equal to, if you are neglecting the inertia of the system, you can write the equation motion in this form. So, F will be equal to the force vector will be equal to your stiffness matrix into this displacement vector. So, if you are writing in this way, so this is the stiffness formulation method, or you may write this equation x equal to 1 by k into F. So, here 1 by k I can write equal to A. So, this will be equal to AF. So, this A matrix is known as the displacement influence matrix of the system, and the coefficients of this matrix are known as the coefficients of the influence coefficient matrix. So, coefficients of the displacement influence coefficient matrix. Similarly, the coefficients of this K matrix are known as the influence coefficient of the stiffness matrix. So, first let us find or define this flexibility influence coefficient or the elements of this matrix A. So, Aij, that is flexibility influence coefficient. So, this is known as flexibility influence coefficient. So, Aij is known as the flexibility influence coefficient, and it is defined as, so it is the displacement at I. So, it is defined as the displacement at I due to unit force applied at J with all other forces equal to 0. So, this flexibility influence coefficient Aij is defined as the displacement at I due to unit force applied at J while other forces are 0. So, we can take a simple example of a spring. So, let us take two springs. So, this is one spring and this is the point where it is connected to another spring. So, let us find the influence coefficient of this system. So, let K1 is the stiffness of this first spring and K2 is the stiffness of the second spring. So, in this case the influence coefficient A11, so that is displacement at 1 due to a unit force applied at 1 when the other forces are 0. That means, when a unit force is applied at this position, but there is no force at this position. So, what is the displacement at this point? So in that case, this is a simple spring where a force, unit force is acting on the spring. So the displacement will be equal to force by the stiffness of the system. So this A11 will becomes 1 by K1. Now A12, so A12 equal to, so displacement at 1 when we are applying a unit force at 2. So a unit force is applied here. So if I am applying a unit force at this position, so I have to find the displacement at this position. So this will give this A12. So when if unit force is applied at this position, these two springs are in, so these two springs are in series. So as the two springs are in series, then the equivalent stiffness equal to 1 by K. So 1 by K equal to 1 by K1 plus 1 by K2. So this one, so the displacement here, so displacement at this position will becomes, so the displacement at this position we have to find. So this is the displacement at this position. So this is your A22. So A22 equal to 1 by, so this is the equivalent stiffness of the system. So A22 becomes 1 by K1 plus 1 by K2, and we have to find A12 and A21. So when a unit force is applied at this position, the displacement of this equal to 1 by K1, and the displacement as you are not applying any force at this position, so this point will have a rigid body motion. So this rigid body motion will be equal to the displacement at this position. So A21, that is displacement at 2 with a unit force at 1 will becomes same as A11, that is equal to 1 by K1. Similarly, when we are applying a force, to find this A12 we have to find what the displacement at this position due to the force at this position. So when we are applying a force at this position 2, the displacement will becomes equal to 1 by K1. So the same force will act at this position. So the same force is acting at this position as they are in series. So this displacement will be equal to 1 by K1. So this A12 becomes 1 by K1. So let me explain it again. So let us take this system. So in this system I am taking two springs. So in these two springs, so in these two springs the spring constant is K1 here, spring constant is K2 here. So to find A11, so you have to apply unit force here, apply unit force at this position. So if when you are applying a unit force at this position, then the displacement of this will be equal to force by this stiffness. So that is equal to 1 by K1, and due to this displacement, as there is no force acting on this position 2, the position 2 also will have the same displacement. So you can write your A displacement at 2 due to a force at 1. So A21 equal to 1 by K1. Now let me apply a force at this position. So this force, unit force I have applied at this position. So when I am applying a unit force at this position, displacement at this will be equal to the force applied at this position by the stiffness at this position. As these two springs are in series, same force will act at this position also. So a unit force, so 1 by K1 will be the displacement at this position due to a force, unit force at position 2. So this becomes 1 by K1, and A22 will become, so when the force is acting at this position, so this will be equivalent to a single spring with equivalent stiffness K. So this equivalent stiffness, you know, it is equal to 1 by K equal to 1 by K1 plus 1 by K2. So you can find this K, and this 1 by K is the displacement at this position. So this is equal to 1 by K1 plus 1 by K2. So in this way you can find the influence coefficient or flexibility influence coefficient of the system. So the flexibility influence coefficient matrix becomes, so 1 by K1, 1 by K1, then 1 by K1, K1 plus K2 by K1 K2. So, I have added these two. So, when you are adding these two, 1 by K1 plus 1 by K2, this becomes K1 plus K2 by K1 K2. So, in this way you can find these influence coefficient of the system, simple system. So, let me take another example to find the influence coefficient. So, let me take a simple cantilever beam. So, in this cantilever beam, let I have 3 masses attached to this cantilever beam. So, in this case I have to find the influence coefficient. So, influence coefficient A11, let me find A11. To find A11, so I have to put, so let me position this, let this is position 1, this is position 2 and this is position 3. So, in if I have to find this A11, I have to apply unit force at 1 and find the displacement at 1. So, if you will apply unit force at 1, so to find the displacement at 1, I may draw this bending moment diagram. So, from the bending moment diagram, area of the bending moment diagram, I can find the displacement. So, the area of the bending moment diagram, let me draw. So, the bending moment will becomes the bending moment diagram, this is the bending moment diagram when a unit force is acting on the system. So, this length equal to, let me take equal length. So, this is L, L and L. So, this length becomes 3L. So, this is 3L, as I am applying a unit force here, this bending moment at this position also becomes 3L. So, this bending moment is 3L and this length is also 3L, and I have to find the displacement at this. So, by using this area moment method, so by area moment method I can find the displacement at this position. So, this is equal to the moment of the area of this by EI. So, moment of the area, so this area becomes, so this becomes half, so this becomes half 3L into 3L. So, this is 3L into 3L is the area, and I have to take the moment. So, the moment, the center of this is at a position here. So, it is at 2/3 of this. So, I have to write this. So, this becomes, so A11 becomes, so 2/3 of this length equal to 2/3 of, so it is at a distance 2/3 of 3L by EI. So, this becomes, so 2 cancel, 3 cancel. So, this becomes 3 into 3 9. So, this becomes 9 L. So, 9 LQ by EI. Similarly, you can find A21. So, A21 is nothing but, this is the displacement at position 2 due to a unit force acting at 1 when other forces are 0. So, in that case the bending moment area diagram will be this. So, this is the, so you have applied a force here and this is the bending moment area diagram. So, from this you can find the A21. So, A21 becomes the, so A21 you can find it is equal to 14 LQ by 3 EI. So, similarly you can find A31. So, A31, for finding A31, so you are finding the displacement at this position. So, this is the position 3 you are taking. So, you are finding the displacement at this position, and so for this position this, so let me write this. Okay. So, for this area you can find the area of this. So, this area you can find in many different ways you can find. So, let you draw. So, this is a rectangle plus this triangle you can take, and in this way you can find. So, A31 you can find, similarly it will becomes 4 LQ by 3 EI. Similarly, you can find when you are applying a load at position 2. So, you can apply a load at position 2, you can draw the bending moment diagram. So, in this case the bending moment diagram will be, this will be the bending moment diagram. So, this bending moment diagram, so this length is 2L, so this becomes 2L. So, you can find the area. So, at different position, when you are finding at different positions, so you can find in this from this area moment diagram. So, in this case you can find a 1 2. So, this is displacement at 1 due to load at 2. So, at 2 position you are applying, at 2 position you have applied a unit force. So, you can find a 1 2. So, a 1 2 you can find equal to 14 LQ by 3 EI. Similarly, you can find a 2 2. So, in this case a 2 2 will give you this area, and by EI, moment of this area by EI. So, that thing you can find it equal to 8 LQ by 3 EI, and similarly you can find a 3 2. So, this is equal to 8 LQ by 3 EI. Now, for the last case, so you can apply unit force at position 1, position 3, and you can find a 3 1. So, if you draw the bending moment diagram, so a 3 1, so a 3 1 will becomes, so a 3 1 equal to half. So, this triangle you know, so this is L, bending moment will be L. So, this becomes L into 2L plus, so this length is 2L. So, this 2L plus, so it will the moment, so you have to take the moment as you are finding from this position. So, you will take it is equal to 2L plus 2 by 3L, and by EI. So, this becomes 4 LQ by 3I, and similarly you can find a 3 2. So, from this triangle you can find for this position. So, this will becomes 5 LQ by 6 EI, and finally you can find a 3 3, this is equal to LQ by 3 EI. So, in this way you can determine this influence coefficient matrix A. So, this will be equal to LQ by 3 EI. So, this becomes 27 14 4 14 8 2.5 and 4 2.51. So, in this way you can find the flexibility influence coefficient matrix of a system. So, today class we have studied about the 3 degrees of freedom systems. We have found the eigenvalue and eigenvector. I told that this eigenvector can also be determined from the adjoint matrix. So, for a given system M K, so you can find first the A matrix. So, A matrix will be equal to M inverse K. So, after finding this A matrix you can find the eigenvalue and eigenvector, and you can find this eigenvector by using this adjoint of A minus lambda I, and you can find this eigenvalue by finding the determinant of A minus lambda I equal to 0. From this characteristic equation you can find the eigenvalue, and after getting this eigenvalue and eigenvector you may find the free vibration response if the initial conditions are known. And then I told you about another method of determining the equation motion. So, that is the influence coefficient method. So, in this influence coefficient method today only we have found, or we know how to determine this flexibility influence coefficient. Next class we will see this reciprocity theorem, and we will find this influence coefficient for a stiffness matrix, and we will determine the response of the system, free vibration response of the system using these influence coefficient methods. Also we will study about the modal matrix method to determine the response of the system. So, we will determine the free and force response of this multi degrees of freedom system by using this modal analysis method, and then we will see some numerical methods or some approximate methods to determine the natural frequency of a system when it is more than, when the coordinates, minimum coordinates is more than 2, or for a multi degrees of freedom systems. Later we will see the numerical or approximate methods to find the natural frequency.